Okay, in this video, I summarize exercise 4, acceleration and rate of the change. We already went over these exercises. For those who are online, this is serve as a summarize. And if you have trouble with these answers, just let me know. I just go over this again. The first question, conceptual question, true or false? Speed is how fast an object travels. Obviously, it's true. And the second one, what is the difference between speed and the velocity? Well, velocity includes information about the directions. Well, speed is a scalar quantity, which means it's just a positive number, how fast it is. Like 85 miles per hour, that's the speed. Well, if you say, well, 85 miles per hour northeast or east of north 35 degrees, that's you're talking about velocity. So, number 3. Acceleration is the rate of velocity changing with time. And also, using normal words, it is how fast velocity changes. Number 4. What is the acceleration of a car? With this, simply the velocity change is 0 to 15, and that's within 10 seconds it changes 15, so its acceleration is a velocity change divided by the time. So therefore 15 meters per second divided by 10 seconds. So that's 1.5 meters per second squared. So, and that's pretty straightforward. And this we went through in the class if you look at the notes. And again, this is acceleration, number 5, acceleration, then 80 miles per hour in 3 seconds. What is the acceleration in units of meter per second? This is again 80 miles per hour divided by 3 seconds, but this time you need to convert to units, convert miles to meters. Basically 1 mile is about 1.63 kilometers, and then kilo means 1,000, so then you convert that to meters. And then hour divided by in the bottom is 3,606 seconds. So they divide. Then you have meters per second squared. And the exercise solving problem, this is continued. And this exercise as well in the assignment, I ask you to actually do a experiment like what we are doing, where we drop a tennis ball from 2 meters down to the ground, and then another student will hold the stopwatch, which is available from your cell phone, and just try to practice a couple of times, see how long time it takes to drop this many seconds. And then if you get the time, and then you can use the 2 meters divided by, say you get 0.8, then you get divided by the time. You get an average speed. And then I went through this in the class, and why this we want average time? Because it changed to the velocity change. It is an accelerated motion. It goes from 0 to final speed, and then the change is delta v. So then the initial speed is 0. So therefore, and then the velocity change is nothing but the final speed. But the final speed, we cannot actually directly measure the final speed unless you have other instrument. But we use this one relation. So the final speed plus initial speed divided by 2 is the average. But we know the average and we know the initial speed. In this equation here, we can find out that the final speed is nothing but average speed multiplied by 2. So why do we need that? We need velocity change. So then once we have that, and we have acceleration, again velocity change divided by the time, and this time velocity change is 2 times of the average, okay, linked to whatever we can directly measure. So then average times 2 divided by this. So we calculated this and plugged this number over here, and then we did, and in this particular case, 2.5 times 2 divided by 0.8, and then you get acceleration in this case is 6.25 meters per second squared. Obviously, this is just an example, and this 0.8 is a fix, and so is this one. Okay, you need to find some object, do an actual experiment. That number you get, and do all this calculation, plug into this formula, and then plug into this formula to get the acceleration. That is a g, okay, acceleration of gravity, and anything that drop down to the earth accelerating at the same rate, and that rate is what you are calculating. Okay, and accepted rate is 9.8 meters per second squared, and you just do the honest accelerations, honest measurement, the calculation. See if you get how close you can get to that that actual number. Okay, number 7. How far does a free fall object fall in 1 second? How about 2 seconds? This is actually a realistic question. You know, you hold a basketball and you drop from a top. Let go and count 1 Mississippi, 2 Mississippi, and which one know 1 second how far it goes. And this will follow a formula. Okay, we're not going to derive that formula, but I just gave you a formula in this course. And then, of course, if you want interested in how that formula came around, and then we can have a discussion offline. But now, where it came from? Recall that in the class we had this falling object, and just recall this problem. And the distance you traveled is follow this formula. Distance is half acceleration times t squared, not t. Okay, and in this case the acceleration is 9.8. But if it's not, it's like a race car or any other thing accelerating on an air track or something accelerating, it will have whatever corresponding acceleration in this place. But in this case, it's a free falling object, which is 9.8. So our formula is distance falling down, you have times acceleration, 9.8 times t squared. In fact, these are summed up in this page. Distance is half a accelerated motion t squared. That's accelerated motion. And besides, we already talked about in the previous class, and d for the uniform motion, if there's non-acceleration or just regular motion with a constant speed, the distance in contrast will follow this formula: velocity times t, or speed times t. So this is the linear motion. But if you combine these two motions, if you have an initial speed, you give a push, and then at the same time accelerating, then you will have an equation down here, which means if you give initial speed, and that's the part of the initial speed, and this part is accelerating, you combine these two. With that, we back to number 7. So, and the distance half at squared, and a replaced by 9.8, so 1 second, so it will have 1 squared times 9.8 times half, it will have 4.9 meters, and that is, that's good to know. So what does that mean? So if you let go of a tennis ball or basketball or some weight, okay, everything drop with the same way, anything, in 1 second it drove about 5 meters. But then you plug in the equation again, how about 2 seconds? So you think it would be 10 meters? No, it's not double, but it's like more than tripled. Okay, so half 9.8 times 2, but this time squared, and that's 4. You do this math, okay, 2 cancels out with 4, and then you will get 19.6. All right, see, if you look at here, and first second was here, 1 Mississippi, 2 Mississippi is going over there. So 1 second go to 5 meters, and second it will go to 19.6 instead of going to 10. So if it would be uniform, it would have been in 10. But in this case, it went to 4 times more. Okay, and 3 seconds, and it was 9 times more. Actually, 41. So that's very long distance. So it follows this at squared. So now question number 8. If you throw a ball straight up imagine, or you can just kick a soccer ball or volleyball going up with some speed, or kick it down. In this case, throw it down. Give it a push, because free fall is just like above. If you give it a push going down like this, and then it will have a first boot, start with, and then it will use a combined formula like this. So you have, if you just with start speed, it will go like this formula. Then you have start with velocity v times t. If there's no acceleration, you just follow this formula. But if there's only acceleration, you follow this formula. But if you have an acceleration and also have an initial start, and you have this two-term formula. So therefore, our equation is half mt squared, like in the previous question, and then you have two, and that's already there to begin with. It's like you throw a ball downwards, so you have an initial push. So then that is this formula. So what is it? And in 1 second, it will drop 4.9. So that's from first game, and 2. So that's 2 times 1. So it's 6.9. Instead of like 4.9 in the above question, here we have 6.9. And 2 seconds, so let's see, 2 seconds is 19.6 first term, and this 2 times 2 is 4, 19.6 is 23.6, so 2.6. So in 2 seconds, let me do one more question. So if you plug in 2, if you do the math, it's 23.6 meters, okay, instead of 19. Because it has an initial push. Okay. Well, in the last question, we use the same formula, but a very interesting way. This follows number 9. If you throw a ball straight up, okay, and with initial speed of 10 meters per second, okay, in reality we know that it will go up and then go down. So, but that it will still cover with the same formula, like this one. So you have the initial speed, except that this one, if you say positive direction is downwards, usually it's supposed to go down, and then you go upward speed, we'll take that as negative speed. So then you will have an equation like this. So then you will have the equation go down here, upwards. So now here, d gravity and the negative 10. So the same equation, but there's a negative 10 initial speed. And then see if you have 1 second, you go through this question, it will going to negative 5.1. And in this case, it's actually going up. It's actually going up. It's actually going up. And then if you after 2 seconds, then it will be going back, negative 0.4. And then 3 seconds, and then it go up and down, and then gain speed downwards and go to 14. So, well, it's nothing but a formula. So if you use negative, which means going up, the initial speed is in the opposite direction of the acceleration. Actually, this formula simply covers the same motion. So it's the same formula. So you go up and down. So it actually goes from this location to up and down. Okay, if you have a question, we can have a separate discussion. Hope this helped, and you can work on your assignment 4.